Today I will present my work on reinforcement learning controlled quadruped locomotion, covering gaits from basic trotting to more complex dynamic motions. The presentation covers research background, proposed method, 3 locomotion stages, and a discussion and conclusion. Traditional leg control relies on handcrafted trajectories, dynamics models, and contact schedules, which becomes fragile for dynamic motions. Reinforcement learning offers a different route. The policy maps proprioceptive observations directly to joint targets, while parallel simulation and domain randomization improve efficiency and transferability. Several prior works motivate this study. PARARL demonstrated massively parallel GPU training. Rapid extended this to higher commanded speeds. SYMRL used symmetry-guided rewards to generate multiple gaits, but trained them jointly, conflating the reward design challenges specific to each gait. I view locomotion complexity as a progression. Trotting is well solved, bounding requires explicit phase guidance, and lateral alternating jumping remains an open problem due to its strict left-right alternation and lateral weight shifting. This motivates 2 research gaps. First, existing multi-gait work trains a shared policy, so the reward design difficulty of each gait is not clearly isolated. Second, lateral alternating jump is underexplored, with no existing reward formulation addressing lateral weight redistribution. Based on these gaps, this study trains 3 separate policies. The experiment follows a staged design, trotting as baseline, bounding as an intermediate step, and lateral alternating jumping as the most complex target. Each policy is trained in Isaac Lab and evaluated in MuJoCo. Next, I introduce the method, the hardware and software platforms, the MDP formulation, and the variables kept consistent across stages. The robot platform is Unity Go2, weighing 15 kilograms with 12 actuated degrees of freedom, hip roll, hip pitch, and knee pitch on each leg. Training is conducted in Isaac Lab with 2048 parallel environments using PPO via RSLRL. For validation, the train policy is loaded into MuJoCo zero-shot, keeping the robot model and policy interface consistent, but switching the physics solver. The control problem is formulated as an MDP. The robot observes body motion, velocity command, gravity direction, joint states, and previous action, then outputs joint position targets through a PD controller. The simulator setup, network architecture, and optimizer are kept identical across all 3 stages, so when different gaits show different learning behavior, the differences come down to the design choices specific to each stage, including the reward function, curriculum strategy, and how the observation space is extended. The training setup is consistent across stages. Extra inputs, foot contact state, gait clock, and base height are only added when a motion explicitly requires phase guidance, such as bounding and lateral jumping. Now I move to the first stage, trotting, which tests whether a stable diagonal gait can emerge without explicitly prescribing the contact sequence. Trotting refers to a stable diagonal gait on flat terrain under a commanded velocity. The key insight is that diagonal leg coordination can emerge naturally when velocity tracking, posture stability, mechanical regularity, and foot clearance are properly balanced. Unlike bounding, no explicit gait clock is needed here. The reward contains 4 components: velocity tracking as the primary objective, posture stability to limit body rotation and bounce, mechanical regularization to penalize excessive torque and rapid action changes, and foot clearance to encourage proper swing leg lift. A curriculum gradually expands the velocity command range once tracking becomes reliable. The results show stable learning. The mean reward rises quickly and converges, while the value function loss stays low. The foot contact diagram alternates between FL plus RR and FRRL, confirming a diagonal trot rather than a walking or dragging strategy. The visualization confirms the learned gait. In Isaac Lab, robots spread out under different commands while maintaining the trot. In MuJoCo, the same policy produces the same diagonal pattern without retraining, showing the gait transfers zero-shot across simulators. The second stage is bounding. Unlike trotting, velocity tracking alone can be satisfied by easier gaits like pacing or low-amplitude walking, so explicit contact phase guidance becomes necessary. Bounding requires all 4 feet to support, lift off, and land together under a 0.6-second gait clock. Without this structure, the policy has no incentive to produce a genuine flight phase. The task is decomposed into 3 sub-goals: synchronized 4-foot contact, a clear aerial phase rather than shuffling, and stable landing with recovery into the next cycle. The bounding word compares measured foot contacts with the gate clock. 4-foot contact is rewarded during support, and 4-foot no contact during flight. Feet clearance encourages lift, while a no walking penalty discourages walking like shortcuts. Stability terms suppress collapse and hard impact. The results show the reward increases and stabilizes at a high level. The contact diagram is the key evidence. The 4 feet are mostly synchronized, with clear no-contact intervals corresponding to the desired flight phase. The visualization shows the learned bounding cycle: push-off, landing, retraction, and the next push-off. Both Isaac Lab and Mujoko preserve this synchronized structure, confirming zero-shot transfer. Now we move to the final and most complex stage, lateral alternating jumping. The lateral alternating jump requires strict alternation between left pair and right pair stands under a 1.0-second gate clock. What makes this harder than bounding is the left-right asymmetry. The dominant shortcut is trotting with diagonal contact, which neither bounding rewards nor velocity tracking alone can suppress. The task is decomposed into 3 sub-goals: left-right phase alternation, aerial phase generation, and stable landing. A 2-stage training pipeline is adopted. Stage 1 learns stable ipsilateral alternation via RSI and phase-guided reward. Stage 2 uses AMPU push-the policy from stepping into genuine flight, using Stage 1 rollouts as expert reference. Stage 1 reward covers alternating contact against the gate clock, swing side clearance, and stability penalties. Stage 2 adds an AMP discriminator trained on Stage 1 expert data, which guides the policy to match the lateral alternation style, while task rewards drive genuine flight. New jump-specific rewards are added to incentivize real takeoff and penalize fake airborne behavior. RSI and phase joint tracking both belong to Stage 1. RSI synchronizes each reset to a keyframe in the reference cycle. Phase joint tracking continuously interpolates between keyframes to provide temporal structure throughout the episode. Contact state and gate clock are added to the observation, while base vertical velocity is excluded to avoid discouraging upward motion. Your commands are also fixed at 0 to prevent rotational shortcuts during lateral alternation training. The key insight is that direct jump training is infeasible. Stage 1 must first establish stable alternation before AMPing bridge the gap to genuine flight. The results show a clear 2-stage progression. The policy first converges under Stage 1, then jumps significantly when Stage 2 kicks in around iteration 4000, reaching a much higher reward level. The loss spike at the transition is expected, as the policy is essentially relaying under a richer reward structure. The foot contact diagram confirms the intended alternating pattern, with clear gaps between contact blocks showing genuine aerial phases. In Isaac Lab, the robot clearly alternates between left and right pairs with visible lateral body lean. In Mujoko, the alternating contact pattern and lateral com shift are both maintained 0-shot. With all 3 stages completed, let me now step back and compare the results across the full progression. Looking across the 3 stages, 2 observations stand out. First, different reward ceilings reflect formulation complexity, not training effectiveness. Trotting has no phase contact bonus terms, so its ceiling is inherently lower. Second, all 3 stages start differently. Trotting starts positive, bounding slightly negative, and lateral jump deeply negative, because more penalty terms fire simultaneously from the beginning. To wrap up, let me summarize what this study has achieved and where it can go from here. To summarize, we trained 3 separate policies across increasing locomotion complexity on the Unitree Go 2. Trotting serves as the reference baseline. Bounding required explicit phase contact guidance beyond trotting. The lateral alternating jump demanded a 2-stage training pipeline. Stage 1 used RSI and phase joint tracking to establish stable ipsilateral alternation. Stage 2 applied AMP to bridge the gap from stepping to genuine flight. All 3 policies transferred successfully to Mujoko under 0-shot evaluation, confirming that reward complexity escalates with locomotion complexity. One limitation of this study is that real hardware deployment has not been attempted, so the sim-to-real gap remains unknown. For future work, the primary direction is to unify all 3 gates within a single policy framework, where different motion modes are conditioned on gate parameters rather than trained separately. That's all from me. Thank you.